Please, Hayashi-san, please,
Okay, please start. Please start.
please start. Start.
Okay, so let's start the first session of this workshop. So the first speaker is Harumichi Nishimura, who will talk about power and limitation of distributed quantum proofs.
Thank you for the introduction. First, I would like to thank the organizers for this large effort for this workshop. I also appreciate inviting me for give a talk. My title is the distributed quantum proof. I talked this topic in 2002, 2 years ago and last year. So this talk is I introduced in this talk the new development of this topic. This topic here is quantum and distributed computing or network and proof verification. This is an NP-like proof system. First, I record proof verification. This is typically called considering as P versus NP problem. P is the class of problem that can be computed efficiently. Here, efficient means polynomial time. On the other hand, NP is the class of can be checked efficiently. Of course, polynomial time is help of proof. The formally, yes, no problem A is in NP. If and only if there is polynomial time algorithm V such that satisfying to condition. First condition, completeness. If X, input X is yes instance, then there is a proof or certificate such that the verifier accept or output yes. On the other hand, as another property called soundness, if input is no instance, then for any certificate track string, V reject or output no. This is the definition of NP. For example, the factoring problem, this case, the input is positive integer n and k, and output is yes if and only if n has a non-trivial divisor smaller than k, then certificate corresponding to any non-trivial divisor smaller than k. So factoring is typically is NP problem. Now I consider this NP as communication system. In this case, we have two parties. One is prover or Merlin, other is verifier or author. Prover is send the certificate for the proof, and he is computationally unlimited, so he can create a powerful computer and create a proof. On the other hand, verifier is computationally limited, namely polynomial time. He received W and verified V. W, XW is accept or not. So this one-way communication system is NP. We can consider a little bit extension, randomized version of NP. This is called NMA, Merlin-Arthur proof system. This case, this verifier can flip a coin and use the probabilistic strategy. Now we can consider more extension of NP. First, interactive proof. This case, prover and verifier can interact two-way communication. Another more extension is multi-prover interactive proof. This case, prover are multiple. And verifier can communicate with both or more. On the other hand, prover cannot communicate with each other. This is multi-prover interactive proof system. Another variant is the multi-verifier interactive proof or proof. This case, verifier consists multiple parties. And these guides can interact with prover. In this case, we can consider that verifier cannot communicate each other, but we can consider that party can communicate each other, but the communication is expensive. This talk consider this kind of setting. Now we introduce our setting in classical setting. This is called distributed Merriam-Webster protocol. Sometimes this a kind of variants, but I don't care this variants. Important stuff is input is string. So now verifier consists of network and each node corresponding to each party. And some party called terminal has input locally, X, Y, Z, right? But this is not only the input. We consider another input, this network itself. So the structure of network itself is an input of this problem. And prover sends some certificate like string to each node. This is the first phase. So the prover phase, prover sends some string to each node. And second phase is called verification phase. This case, the verifiers interact by sending a message. The important property is of this setting, also called, we have two properties for completeness and soundness, similar to NP system. But different from NP system, now we have many verifiers. So decision, we must how to decide by parties. For yes case completeness, there is some proof such that all nodes accept or with high probability. This is completeness. On the other hand, soundness case, if no instance, then any proof, there is some party who output reject. This is a property of distributed Merriam-Webster proof system. One of the reasons of why this property is called considering that some network has must be stable by some property. If it's not stable, some party call ring a bell. This type of idea correspond to this property. And now we consider the complexity of DMA. NP case efficiency corresponding to polynomial time. But this case efficiency corresponding to communication bit. The powerful prover means knows all information. On the other hand, verifier consists of each party knows only local information. So the information gap is the difference between prover and verifier. Now, the communication bit consists corresponding to proof size for prover case, so like this. And verifier phase corresponding message between the any two parties. In this talk, I use two types of proof size. One is local size. this is the maximum of the number of bits of proofs. So we take maximum over each string. Similar, we consider the message case. Other case, we consider the total proof size. This is just sum of all proof or all message. Now we move to quantum case. This case was introduced several years ago. Francois, me, and Paz. This is just simply change classical stuff to quantum. First is the certificate is changed to quantum state. And also the message between the node is changed to quantum stuff. So definition is very simple. Now the question is, which problem are efficient in the term of communication for DMA protocol, DQMA protocol? We consider a very simple problem called it. This is a several terminal has string. These strings are equal or not. This is the equality of data. Formally, EQ x1 to xt. This case, T terminal have input, J terminal has xj. Then output equal 1 if and only if all the strings are equal. This is the definition of EQ. Now, I present a very simple protocol, classical protocol for EQ. Now, this case, prover send the string to intermediate node, but if we our input is yes, namely all the data is equal and x, then prover send x to intermediate node. And in verification phase, verifiers check the neighborhood string is equal or not by sending the whole x to each other. Clearly, this satisfies completeness because every edge says yes because x equal x or the edge. On the other hand, if some string is not x, so this and this is different, then any proof is rejected with probability 1. Because, for example, this case, x and x prime, this case, this guy sent some string. If this is x, then this line is rejected. On the other hand, this is x prime, then this line is rejected. Of course, other string is both are rejected. That's it. But this protocol is communication is very high because the proof size is input string length itself, n. But in fact, we show this trivial protocol is optimal. Namely, any classical protocol require local loop size is omega n when error probability is reasonable. On the other hand, this is the main result of this, the quantum upper bound. Quantum case, we show this protocol. Uh, uh, local proof size, also message size, is the order log n times the graph size parameter. Here T is the number of terminal. This case is 3. Also, R is the diameter of network. It's the longest length of the longest path of the network. Roughly, this is the graph parameter, graph size parameter. So the network is small compared to the n input string. Then this complexity is exponentially better than the classical case. So the small network case, we get the exponential speed up in quantum. This is our result. This is the FLNP result. The proof strategy is a bit similar to classical case. So classical case, the prover send the string to intermediate node. For example, this X3, if and all X3, then send X3 to intermediate node. But in quantum case, we can send some exponentially shorter quantum state called fingerprint, quantum fingerprint. And this fingerprint can check the equality or not. This is a well-known result. So we can send the fingerprint to intermediate node. But to check the equality, we consider some protocol. So we consider the fingerprint check by swap test is line network. So we consider this each line for some leader node and other terminal. This have some line. Between these two nodes, we check the equality. So if x2 equal x3, then this line all accept. But this is not equal, then any quantum state, including non-tensor product, some guys reject hybrid. And we extend this line protocol to whole network by using the spanning tree method. It's well known in classical distributed computing. So the prover sends such a spanning tree. So this spanning tree consists of the several lines from the one leader to another terminal. And this spanning tree can be checked efficiently in classical result. So after checking the spanning tree, we run the line protocol in each every line network. This is a rough idea of the FLNP result. Follow-up, as a follow-up work, the Rugal and Miyamoto-san, Rugal's student, and me consider the two types of result setting. First is the distributed interactive proof. So we extend the communication is from one way to two-way. Another is the state synthesis. This case, the yes-no problem is changed to the generation of quantum state. As an application of this state synthesis, we show the another quantum proof system for problem called set equality. This is the previous result. Now, question is, can we have more problems that efficiently verify quantum stuff? And the second main important problem is quantum lower bound. Previous result does not do not have any lower bound, quantum lower bound. So we consider these two open problems. First, we get more problem can be verified in this quantum proof, distributed quantum proof system. I explain this too later. And we get a quantum lower bound. But measure is a little bit different from previous. So we consider the proof side plus message side. I explain this more. First, Hamming distance. This is maybe some of you know already. This is natural extension of equality. So equality case, all data is equal. But Hamming distance case, Ham D. This case, every pair has Hamming distance at most D. For example, here, this three terminal has 1111, 1110, 0001. This case, Hamming distance D equal 1, it is not no output. Output is no, because this and this has Hamming distance 2. So Hamming 2 is yes. All three has Hamming distance at most 2. Previous results show efficient DQM protocol in the line network for constant D using fingerprint strategy. But at this time, this result cannot extend to general network. We are done. There is a DQMA protocol for Hamming D, constant D, such that local proof is small if network is small compared to data size in general. This is the first result I showed. And second problem is ranking verification. This is also a very natural problem. Ranking is a generalization of maximum. So rank Tj x1 to blah, blah, blah is j's largest value in the list of x1, x2 to xt. For example, x1 is 13, x1 to 14. Of course, this is represented by the n-bit integer, in fact. Anyway, 13, 14, 9. This case, the rank first j equal 1 case, this is the maximum, so t equals 2. So, sorry. J equal 1 case, the output is x2, 14. This is the ranking. Now, we consider this NP type question, ranking verification. This case, we consider some node, xi. Question is, xi is the j's largest value in the list or not? Yes, no question. For example, j equal 1 case, question like this. xi is largest value in the list. For example, I equal 1. x1 is the largest value of the list. This case, no. I equal 2. x2 is the largest value of the list. Yes. This is the ranking verification problem. We show this problem has also efficient distributed quantum protocol. And the local proof size is relatively small in general. This is our second result. And we move to quantum lower bound. We show the lower bound on the measure total proof and message size in line network. Line network means that this simple network and both ends has input. In this case, we show this size for problem equality is omega the polynomial of log n. So upper bound is this, the order R depend on R, but the log n. So in terms of n, this is the optimal up to polynomial. Of course, the size is network size is large, then this gap is much different. It's an open problem. In particular, if line is constant, then we can improve this too. So the gap is square in terms of log n. And also we get another lower bound for a famous function disjoint and IP, but I do not explain this, what is the disjoint or IP. Now we show the two results, and we get more results. First is the improvement of the FLNP. The improvement is, for example, local proof size of EQ in general network. The previous result is the complexity is like this. We eliminate this term T using the permutation test. This is the natural extension of swap test, and we show the rigidity of permutation similar to the rigidity of swap test used in this paper. And also we show the quantum advantage of EQ on the line network, even if length is relatively large compared to input length of EQ. In previous in previous case, I already assumed the n data size is much larger than the graph size, but in general it's not. So this and this is relatively same. Even in this case, we get some quantum advantage. More concretely, total proof size is classical case is this amount. On the other hand, quantum case this amount. So we can get polynomial speed up in this case. Now, maybe already 30 minutes passed. In the remaining of maybe about 10 minutes, I give a brief idea. I focus on ranking verification and lower bound for EQ. First, ranking verification. This is essentially the classical reduction to previous result. The proof strategy is very simple. We use a DQM protocol for another function called greater than function in the line network. Here, greater than function is, as name says, this type of function. If x is larger than y, output is yes, 1, otherwise 0. Now we consider this GT function to equation. It's a very simple one. We hit upon this characterization. Namely, GT is equal 1. Then exists some j, xj equal 1, and yj equal 0. And other previous prefix string is same. For example, x is 1, 0, 1, 0, 1, 1, and y is 1, 0, 1, 0, 1, 0, 1. In this case, first four string is same, and fifth bit is this guy 1 and this guy 0. So we can reduce to this GT to this equality and extra information. This can be easily by proof sending. Once we get this DQMA protocol for greater than function, then we can use this function to show ranking verification. For example, this ranking verification is maximum case. For example, this guy is maximum. We run the protocol. This guy is larger than this. This guy larger than this. This guy larger than this in the line network, similar to the FLNP result. This is the rough idea of ranking verification. And the second proof idea of lower bound for EQ. This is more complicated, honestly. The first, we consider this to show the lower bound for EQ. We use reduction, two-party communication complexity. This communication complexity is well studied in computational complexity, but in distributed computing setting, this is a kind of the two-party case. So the just length network is the line of length 1, and terminal A and B has string x and y. And we can verify some function f xy equals 1 or 0. This is the this setting was considered in 20 years ago by Rao and Shapika, and this people call this communication complexity by QMACC, QMA communication complexity. So QMA communication complexity setting is this guy has X, this guy has Y, and these guys want to verify X, fxy equal 1. Then Melodin sends some proof and check this. And the complexity is the length of proof and the bit length of communication. And sum of proof length and communication. And another second concept of our proof is the separable DQMA protocol. This is the special case of the general DQMA protocol, where the proof must be product of state like this. So this kind for party. So the proof is the fourth tensor product state. In fact, the all protocol in this paper are separate because we use the fingerprint test, swab test. Our main lemma is the conversion of general DQMA protocol to separable DQMA protocol. which means that any function has DQM protocol with total proof plus minimum message size of C in the line of length R. Then there is a separable DQM protocol for F with total proof size is like this. Luckily, this for this lemma, for showing this lemma, we use again reduction to two-party communication protocol, dividing two party between the bottleneck. And once this conversion, we get this type simple two-party communication protocol thanks to large and Shafiqi result. So we convert this two-party communication protocol using the best of previous like result. So we extend to general line to and swap-based test. We use swap-based test. Once we get this conversion, then we are enough to show the lower bound on separable case. So we get separable case total proof size omega r log n using some technique. Once this result, we can use our main lemma and get the lower bound for entangled case. And we give another lower bound for entangled case for EQ. This is relatively simple. Using these two lower bound, we get our main lower bound. This is the proof sketch of EQ lower bound. Now, I summarize my talk. We get several results in this time. In particular, more problems can be efficiently verified in quantum Mellin-Arthur proof system. And also, we get first quantum lower bound for EQ and blah, blah. The future work is, of course, this gap is huge. So we want to shrink this. And more importantly, in fact, this lower bound and this upper bound is, the measure is different. Lower bound use a proof size plus message size. On the other hand, upper bound is only proof size. So we want proof size only, lower bound on proof size only. This is very important open problem for me. And another future is the quantum advantage for natural problem. Then network size is relatively large compared to input. Maybe almost time. Thank you. That's all.
Thank you very much. Any questions?
So why is splitting total proof size and message size difficult? Why splitting, total proof size and message size is difficult?
Difficult. So previous result, we consider only proof size measure because this is most important measure we see this type of problem. But for only proof size, we can show more outcome. This time, another important measure, message size. Of course, the message size is also important measure. So we cannot, in the classical literature, they consider the message size also. So we consider the addition of sum of these two measures. But our proof technique is very important, depend on the such a sum. So we use the conversion from general case to separate case. This conversion is need the sum of two measures, not only consider the proof size. That's a need.
Any other questions? So I have a question. So how do you get the 2/3 there in the
This.
yes, this 2/3? How do you get?
This. So this is maybe. So we divide the line to something, and the relay node receives the whole string, and other this part is very short, so we use the FLNP technique. So the trade-off happens this.
Okay, I understand. Yes. But actually, I have another question. So to prove your lower bound, you convert a general QMA protocol into a separable QMA protocol, and you are losing a little bit in the lower bound, right? Your lower bound become weaker. So do you have an example where it's more efficient to use a general and entangled proof than separable proofs? Or a candidate?
Yeah, candidate. This is just
Yeah, I understand. Yeah.
So, yeah, maybe this lower bound should be matched. This is my expectation.
Because generally, a very important problem in quantum distributed computing is to find example where entanglement is useful.
Yeah.
So we may consider the case for this.
But we have not complete example protocol using such a non-separate protocol. All without it separate.
Maybe a conjecture is that it does not help.
Strategy. So yeah, that's a very interesting.
Okay, I think it's a difficult question. Okay, thank you. Any other questions? Maybe online? Okay, we can stop here and thank Harumichi again.
We're waiting for the あ、テスト休みなのか。
So we'll wait until the exact time, so 4 minutes.
Yes, we will wait a few minutes before starting.
Ah, どうするんだ。そうです。確かに。私は。
Okay, so the next speaker, Yupan Yu, and the title of the talk is Space-Bounded Quantum State Testing via Space-Efficient Quantum Singular Value Transformation. Yes.
Okay, thanks for inviting me. It's a joint work with Francois and Zhizhen Wang, and the paper is already on arXiv. We're starting by stating our main results. So it's a new complete characterization of quantum log space from quantum state testing. So the task quantum state testing typically is like given you good quantum states, and you want to decide whether they are close or far. with respect to some distance-like measures. But of course, to talk about it as a promise problem, we need to really not just think about the sample accesses to states. Actually, we need to think about like the quantum circuit for preparing the states. Namely, the circuits Q0 and Q1. And typically, they are like a polynomial size and acts on polynomial many qubits. And this task is a two-sided error case. So there's actually a classical counterpart of this task called the distribution testing. So the task is instead of try to distinguish two states, it's distinguish to distribution. And also there is a one-sided error case, which the task now is like decide either these two states are exactly the same or they are far from each other. So like I mentioned, like typical goal for this task is try to minimize the copy weakness. People call that the sample complexity or copy complexity. But in this work, we talk about like this viewing this quantum state testing as a computational problem, like really a province problem. So our first main result is about the one-sided error case. We call that space-bounded quantum state certification. Task is given to polynomial size quantum circuit. They are acts on logarithmic many qubits, and they are Q0 and Q1, and they produce two quantum states 0, 0, and ρ1. And the task now is to decide either ρ0 is equal to ρ1 or the distance is far. And for the one-sided error case, we talk about actually two distance like measures like the trace distance and also the Hilbert-Schmidt distance. They also have the classical analogs. And the result for this part is we're showing that, in fact, this problem characterizes quantum log space computation with one-sided error. So this strange name unitary call RQL is just the power of unitary quantum log space that always accept for yes instance and accepting no instance with probability at most half. And one remark to make is there are two items in this theorem, but actually the second item is fairly straightforward because as you can see, for this Hilbert-Schmidt distance, essentially we can write it as a linear combination of several terms like the trace of product of ρ0, ρ1, something like that. Then we can verify it by the soft test. So like the challenge is really about the first item. And our second result is instead of just talk about one-sided error case, we also can talk about two-sided error case. Now the task becomes space-bounded quantum state testing. The task is very similar, just to have like a polarized quantum circuits and acts on log-width qubits and prepare like log-width qubit states. And now the task is decide either these two states they are alpha far or beta close. So our second result is essentially this problem characterizes quantum log spaces with two-sided error. And the result is not only holds for the trace distance, gap QST log and the Hilbert-Schmidt distance, but also for the quantum entropy difference. Namely, here we are using von Neumann entropy and also the distance version of the von Neumann entropy. So as it's very easy to guess like this class BQL captures the power of quantum computation with logarithmic many qubits. Right. And then I'm going to compare this space-bounded testing task with the usual time-bounded testing task. So we can define a time-bounded quantum state testing task. It's like also given two polarized quantum circuits. They are prepared like corresponding many qubits, and to decide either they are alpha far or beta close. And so typically for this time-bounded setting, the L1 norm actually is very easy, as we already saw. Is you can use some technique based on soft test. But the L1 norm case actually is corresponding to a different class. We call that QSAK in the quantum setting is for quantum statistical zero knowledge, but you don't really know the class. So the only thing you need to know is this class is similarly much harder than BQL. But in the space-bounded setting, what we showed is actually all this testing problem with all these distance-like measures, they're corresponding to the same class. So that's the main takeaway in this part. So for space-bounded state testing and certification problems, the computational harness for these problems actually is the same, just as easy as preparing the states. So that's the main result. And one implication is essentially we can, using the result I just mentioned, actually we can show there is an algorithmic version of the high-level Hailstrom measurements. Right. So now we talk about something similarly more nature task. Now it's not space bounded. So we call that computational quantum hypothesis testing. The task just given to polarized quantum circuit. They act on exactly n qubits and they are output like r qubit states. So like the row, we can think about like row 0 and row 1 to be the state obtained by performing the circuit Q0 and Q1 and tracing out the non-output qubits. And now the task is really the given input, which is a quantum state. Problem is that either row 0 and row 1, which is chosen uniformly at random. And output is just a single bit B, indicating that the state we have is either row 0 or row 1. This celebrate high-level Hailstrom bound telling us for this task, the maximum success probability to distinguish them actually is half plus half times the trace distance between these two states. And if we actually there's underlying optimal measurements behind this high-level Hailstrom bounds. Particularly if for instance, if the measurement outcome is 0, we have this pi 0, and it can be written as identity over half plus half times applying the sign function on the single value of this difference between the state row 0 and row 1 divided by 2. And it's easy to verify that the trace distance between row 0 and row 1 can be written as the difference between these two measurement outcomes. This term pi 0 acts on row 0 and take the trace, and pi 0 acts on row 1 take the trace. And of course, here is the exact version of the high-level Hailstrom measurement. And our work actually showing that there is, so you can really implement it. There's a approximately implementation. So, right. So what we implement actually is instead of really implement this measurement pi 0 and pi 1, we implement this tilde pi 0 and tilde pi 1. And it's guaranteed that using our approximate implementation, the error is could be exponentially small. I mean the difference between the measurement on these quantities with the trace distance is at most exponentially small. And the implementation of this quantum circuit is acting on like the linearly many of qubits, and also requires polynomial of the dimension queries to the circuit Q0 and Q1. So here dimension capital N just to the N. And also the circuit description of this algorithm can be computed in deterministic linear space and like a single exponential time. So the proof sketch is really using the main technique in our paper called space-efficient QSVT. And actually the same technique is also used to show, in particular for the quantum state testing problem with trace distance, is using this technique with sign function. And the quantity now we think about is like for instance, this hat pi 0 is just the identity over 2 plus half times, it's not exactly the sign function, it's a polynomial that approximates the sign function on the difference between these two states over 2. And once we have the unitary corresponding to this polynomial like applying this polynomial approximation to the difference between these two states, then we can using some standard technique called the Hermite test to implement that measurements. And the last part of this talk will be talk about a little bit about how we get the space efficient variant of the quantum single value transformation. So many people maybe heard about this technique, I guess, but maybe only a few people know this. Quantum singular value transformation is a systematic approach to time efficiently manipulating the singular value problems, singular value of the emission matrix is proposed by Gin, Su, Law, and Vibi. On a very high level, is kind of a magic technique that telling us that if you really want to design a quantum algorithm, you don't really need to know the quantum thing. So because like many of the quantum algorithm can be viewed as applying some function on the singular value of the associated encoding. And then the only thing we need to do is find a good polynomial approximation that approximates this function, which is really a classical task. So in a more technical term, we can write a theorem. And so theorem is like now we have some encoding about emission matrix, and we'll think about the singular value decomposition of this emission matrix. That's why we have the singular values. And we want to approximately implement a QSVT, namely the singular value transform on this encoding. And this polynomial, of course, have limited degree. And we want this polynomial, we know it's approximates a function of interest, but we would like this polynomial to have two property. So first, it will be this polynomial will well approximate the function on the interval of interest. So basically, most of interval from -1 to 1. But maybe we're also allowing the approximation is probably very bad on a very tiny interval, for instance, around the original point. And the second is we want the polynomial is really bounded by 1. So now the task is apart from finding the polynomial approximation, we call that preprocessing. The task is to compute the coefficient of this polynomial. And in the original technique of QSVT, it can be done in the polynomial of the degree time. So that's the natural space upper bound. And but the other part is the transformation. The quantum part is like once we have this polynomial approximation, and we can implement this QSVT using a polynomial of degree size quantum circuit, but acts on only a number of qubits, which is almost linearly on the size of the encoding. So actually, the second part is telling us the quantum circuit implementation in QSVT is already space efficient. And the challenge is really like how to find a good polynomial approximation. So now I'm summarize the question. We need to address it. So the question is how to implement this space efficient QSVT. So typically we want to, typically it's like we consider the case like we have an encoding. It only acts on logarithmic many qubits. And we want to implement a degree T QSVT. So here degree is a polynomial. And using only logarithmic space in both pre-processing, namely the part for finding the good polynomial approximation, and also the quantum circuit implementation. We want to do that at the same time. So the partial solution actually is already hinted in the original paper, because for a particular function called Chebyshev polynomial, indeed we can do the pre-processing part even analytically. This intuition is even underlying the GRU research. And just using the original paper, we can do a space efficient QSVT for this particular Chebyshev polynomials. So then we can guess like a natural approach is somewhat projecting the function of interest onto the basis formed by the Chebyshev polynomials. This is essentially achieved by Matijan and Yuan. And they are talking about some functions with very good property, like the continuous function bounded on the whole interval from -1 to 1. And there's a few limitations in their techniques. The first thing is this pre-processing part, namely the part finding polynomial approximation requires not just the logarithmic space, actually need polylog space. Second thing is approximation error, which is directly caused by the polynomial approximation on the interval of interest will be increased from epsilon to the big O of epsilon log times log D. This is because of the property of the Chebyshev truncation. So in our work, we solve this problem. So we propose a technique called space efficient QSVT, which can approximating like the function is not just with this very good property like continuous function bounded on the whole interval. Actually, we can also dealing with something called piecewise smooth function. So one example is like you can think about is like a normalized log function, just a log function, and we don't care about the part which is very close to the original point. And so we improve the preprocessing part from the polylog to log space to log space. And also the polynomial approximation error on the interval of interest now can be reduced to the big O of epsilon. So the implementation of this space efficient QSVT requires like the d squared times L1 norm of the coefficient vector C uses of the unitary, actually the encoding and the controlled projection. And so here the L1 norm of C actually is bounded by log D. And actually for the most function we talk about in this paper, the bound is constant. So that's what I talk today. I'll summarize what I'm talking and mention a few open problems. And so the take-home message for our work is we're really talking about this space-bounded quantum state testing problem with one-sided error and two-sided error. And for two-sided error case, is a new family of the complete problem for the class BQL captures quantum log space computation. And for one-sided error is also a complete problem, which is actually the first family of the nature problem of the complete for this one-sided error class. And one particular application for our technique beyond the space-bounded computation is we can approximately implement this level Hailstorm measurement for distinguishing two quantum states with respect to the trip distance. And this implementation required the time complexity is a polynomial of the dimension and the space just linearly on the number of qubits. So I didn't mention it to talk, but actually is using this, you can show like the class QSAK is contained in two message quantitative proofs. With honest prover, the power is no longer like the unpowerful. But here is actually only have limited power like quantum linear space. The last thing is we propose space efficient variant of QSVT, and yeah, and it have basically everything in log space. So the open problem is first is do we have other application for this technique space efficient QSVT? Because it feels like it's like one of the fundamental technique for space-bounded quantum computation. For instance, we can easily do the error reduction for unitary quantum log space using our technique, but before that, it actually is worthwhile to write a whole paper for this task. And another question is, so in this talk, we'll only talk about space-bounded quantum state testing. So one nature and a more generalized question is, what about the space-bounded quantum channel testing with respect to different distance-like measures? Do we have still the similar phenomena like they are all BQL complete regardless the measure we are choosing, or maybe there still some difference? So that's one.
Any questions? I have one question. Why is classical preprocessing randomized and not deterministic?
Okay, it's depend on the function we are talking about. So as mentioned, we are dealing with piecewise smooth functions. So if if we only want to dealing with this continuous bounded function as Metiger and Yuan, actually the technique is the whole processing is deterministic. But to dealing with a piecewise smooth function, we cannot do that. There's a reduction from this to, I think it's truncated Taylor series, something like that. And the reduction is using matrix, but I think the powering of some stochastic matrix. This task is only can be done deterministically in polylog space. But to really do that in log space, we need to using random work. Then that's the reason why here is randomized. Actually, so one of the open problem is could we make this randomized part deterministic?
Okay, thank you. Any other questions?
Candidate application, you mean for this problems? Oh, for QSAT. Actually, I don't know. I mean, for immediate application is of course we can think about quantum state testing with for instance fidelity. Definitely this can be done in BQL and maybe other distance like measures. Also, I guess all this older results established by Amon-Tashma and Furman and Lin, I think we can reproduce the same thing using specific QSVT and have, I think, a better time complexity. Beyond that, I don't have like a particular application that looks like very surprising. But
Any other questions? Yes.
So what is the exact condition for the distance like measures listed here? Because like quantum entropy difference is not in general like
okay,
a
so
distance, right?
okay, that's okay. Yeah, the question is why I'm calling that, not really calling the distance. I calling that distance like measures. So I think you're asking related to this page, right?
Yeah.
Okay. Right. So yeah, we are not really dealing with distance. We are dealing with that's why I'm saying this distance like measures, because like for the quantum entropy difference is not a distance. And if we really want it to be a distance, we need to define something called the quantum Jensen-Shannon divergence. The definition is like, right, the definition is like something like that. So actually we can show this quantum Jensen-Shannon divergence is, I think it's a square root of a metric. So this thing is really a distance. That's the first item in the theorem.
I see. So the point is you can construct some distance like measures. That's why the evaluating force QJS and is kind of
So
similar
actually
to
the
3D.
proof for the third item and the fourth item is we have an algorithm to really estimating the von Neumann entropy. The procedure is using QSVT with this normalized log function.
Okay.
And using this, we can show, for instance, entropy difference and also this task. It's a quantum Jensen-Shannon divergence.
Can you say similar things for like relative entropies because there's Pinsker inequalities?
Which entropy you are talking about?
Relative omega key relative entropy.
I don't know. I guess it depends
Just
on
Kalbach-Kleiner, divergence.
I guess it depends on do we have a good polynomial approximation for the functions?
Oh, polynomial.
Yes, because like for instance for this for Neumann entropy is like really the definition is like rho and is minus. So here to approximate using QSVT, we need like the polynomial about this function. And yeah, I think we have a recent work to dealing with the other entropy called the Sallis entropy. It's like it's 1 minus something like that, but it's using a different polynomial. And of course, it's probably applied to other entropies, but really depends on the property we have about the polynomial approximation.
Oh, but the relative entropy is just, or between rho and sigma is trace rho log rho minus rho log sigma, right?
Rho log. Or maybe we can discuss later. It sounds like a bit technical.
Any other question? Maybe online? If not, we can thank Japan again. So I think the next talk will be an online talk. Is the speaker here?
Yes, I'm here.
Yes. Could you please share your slides?
Mhm. Can you see the slides?
Okay, we can see.
Ooh. Mm. Okay. Mm.
Okay, this looks good. So we will wait just 2 or 3 minutes before starting. Okay, so the last speaker of this session is Dong Yang, and the title is Reliability Function of Classical Quantum Channels. So please start.
Okay, thanks. First, I want to thank the organizer for inviting me to give a talk here. The title is Reliability Function of Classical Quantum Channels. And this work is based on a recent paper uploaded all the archive. So this is the outline of the talk. In the first part, I will introduce the channel coding, and then the main result, and then the sketch proof, and then give a brief summary. So let's look at what is a CQ channel. A CQ channel is a map from the alphabet set to the quantum state space. And we can use a CQ channel to generate CQ state that is of this form, where the state hat X is an orthogonal basis, and P here is the probability distribution or the alphabet set. Also, in this work, we limited to the finite alphabet set. So first, let's consider the guess problem, which is the following. So, given suppose Bob is given a quantum state rho X chosen from a state set with probability distribution here with the probability distribution P, and the task is to for Bob is the task for Bob is to guess what the label X is. To infer the X, Bob would like to perform a quantum measurement, and in general case, since the rho X is not orthogonal, then Bob cannot determine X perfectly. So the optimal average error probability is given by this formula. Here, the gamma X is a quantum measurement, a set of positive semi-definite operators such that the sum is the undefinite operator or the curve space of B. Now then, what is the channel coding? Indeed, it is simple to consider the single use of the channel. Let M be the setter message, and let the encoding be E, that is a function from M to the input alphabet set X. And a code is a subset of the alphabet set X, and decoding is perform measurement that show the result of X. So observation is that a CQ state with uniform distribution over a subset of X defines a code, because in the channel coding we require that the distribution of the message is uniformly distributed. Then the minimal average error probability of the code is given by this. Here we have to, yes, this is the minimal average error probability for a particular code, C1. The art to transmit information reliably is to construct codes over multiple use of the channel. So here is the n use of the channel. Input is a sequence xn, and output is a product x rho xn. And yes. And the former picture is directly extended to the block codes. Here, the set message M is denoted by M, and the code is the block code is chosen from the power set X. It is a subset of the power set Xn, and the rate is denoted as the size of the code. Also, the minimal average error probability for the for this particular code is given by this formula. Also, we denote the related CQ state at this one here. I would like to remind that this is a particular CQ state in the sense that the classical part is uniformly distributed. And indeed, in the theory of communication, the central function is the trade-off between the error probability and the rate. Here we take here the error probability for the channel at the communication rate R with n use of the channel. It is defined as the minimal average error probability over all possible codes. So the question to ask in communication theory is the following. First, of course, the capacity. That is the question: what is the maximum rate to reliably send the message? Here, reliably is translated into the minimum average error probability 10 to 0. And if we can show that this is the maximum rate that can be achieved, if we can show that if the rate is above this, is above the capacity, if we can show that the error will tend to 1, this is called strong converse. Of course, if we can show this, and we want to refine the behavior of the decaying behavior of the error probability with respect to the number use of the channel, we would like to ask what is the optimal exponent of the decaying here in the achievable part and here in the unachievable part. Accordingly, we can define the reliability function in the achievable part when the rate is below the capacity. The error probability is expected to decay exponentially. So the optimal exponent is defined as the reliability function. Similarly, we can define a strong converse exponent when the rate is above the capacity. It is called the strong converse exponent. And this is the picture or the known result about the classical channel. And indeed, this topic dates back to the early or the beginning of the classical information theory. And this topic was studied by the founders of the classical information theory. So this is a picture of the known result. From here, we can see that the strong converse can be characterized neatly. But for the achievable part, it is quite complicated. But anyway, we know that if the rate is above a critical value and below the capacity, we can determine the reliability function. That means the optimal error exponent. So then, why do we care about the setting of classic quantum channel? The reason is that arguably it is the simplest case for to involve quantum state. Because here for a CQ channel, this would mean that we would avoid possible non-additivity due to entangled input. Another reason is that though it is simple, but it is very basic or fundamental because it involves the quantum essential features, non-commutativity. Before I list some known results about the CQ channel, we need some notions or functions or quantum Riemann entropes. Indeed, there is many different variants of quantum Riemann divergence corresponding to the classical Riemann divergence. And we know at least two versions of this that has operational interpretation. One is the Petz version defined in this form, and the other is the sandwich version defined in this form. And here, when the alpha is equal to 1, we can obtain the von Neumann entropy. With the quantum Riemann entropy defined as the former slides, we can define the quantum Riemann mutual information by taking the minimum over the divergence. And also we can define conditional entropy. And in this talk, this is the quantum Riemann information of quantum channel can be defined by related the CQ state generated by the CQ channel. Then the node result for the CQ channel is that the capacity is given by the famous Hillel-Schumacher-Westmoreland theorem. It is of this form. And strong-converse exponent is solved by the work Massoni and Nagoya. They gave the strong-converse exponent at this formula. As to the reliability function, I mean, in the achievability part, we only know the upper bound that is given by Dali in this form. Note here the Riemann information of the channel take different form in the strong converse part and the achievability part. So the missing part for the reliability function is a tight lower bound. Indeed, this lower bound is conjectured by Hillel more than 10 years ago. It had this form. If you compare the upper bound and the lower bound, the difference is that only the difference is only the parameter range. In the following, because we only cared about the Petz version Riemann information of the channel, we denote I alpha, D alpha as the Petz version. So the main result is that we can obtain a lower bound, a tight lower bound for the reliability function. here, indeed, this is the reliability function. The left side of this equality is the definition of the reliability function. And the right side is the drainage information for the CQ channel with respect to the probability with the input distributed according to P. Here P is the probability distribution. After we derived this equality, we can, because this equality holds for any alpha in this parameter range, and for any probability distribution, then we can take the optimization over the probability distribution P, and take the optimization over the parameter alpha to obtain the whole level conjecture. And combining the upper bound and the lower bound, we can obtain that there exists a critical value such that when the rate is above the value, but it is below the capacity, we can determine the reliability function given by this formula. Indeed, if we have theorem 1, I mean the tight lower bound, the theorem 2 is can be obtained by standard argument. So in the following, I will focus on the proof of the tight lower bound. So any questions so far?
Sorry, I have one comment. So please back to, so you mentioned that strong converse derived by motion in Nagaoka.
Yes.
But there is no paper, motion has no paper with Nagaoka, I think. This is Ogawa, I think.
Ogawa. Ah, okay. Sorry, I'm a mistake. Yes, yes, you're right. Sorry. Okay, right. Okay, thank you. So in the literature, there are two approaches to obtain lower bounds. One is a direct approach, that is to analyze directly the decoding error probability by using some trace by use of inequality of trace inequality of operators, then applies random coding and such like things. But by far, many works in this approach cannot provide tight lower bound for general CQ channels. But for some special channels, yes, this approach works. For example, if the output state is pure, or in the classic case, the output state commutes with each other. There is also another duality approach developed just 2 years ago. It is developed by Renus, and I should note that Renus' independent work of this one also proved the tight lower bound. So what is the duality approach? And indeed, the duality approach says the duality between the data compression with quantum side information and privacy amplification. from the duality of these two protocols, we can obtain the performance, or we can obtain a good data compression code from a good privacy amplification code. And indeed, in this way, Reynolds in Reynolds' paper, he obtained the error probability for the compression protocol. The lower bound for this error probability is given by this formula. This is the known result. And of course, I said that the duality, which is about how to obtain the this inequality. Now, if we have a good code for data compression, then we can convert a good data compression to a good channel code. So the operation is simple. As we have said in the previous slides, when the classical part in the classical quantum system is uniformly distributed, a good compression code can be translated into a good channel code. This is the case for a single shot setting. So here, suppose X is uniform distributed, then we can divide X into two parts. One is the head part and one is the tilt part, such that this state can be rewritten as this form. And then the left side of this equation measures the error probability of the data compression with quantum side information. And if you express it, then it can be it is the average over the right side. And each term in the right side is the error probability for a channel code. Because here the classic part X hat is uniformly distributed. So from a good data compression code, we can obtain a good channel code. So in the so for the block code, it is easily general to the n-copy case. That means we can obtain the a good block channel code from the data compression code. And indeed, the approach works for a special class of symmetric channel. That means the output state is related by a group, but usually it does not work in general. The reason is that usually the exponent is given by the optimization over probability distribution that is not necessarily uniform. So to make it work, in general, we need a new ingredient that we call the approximation of linear information. Before I state the the approximation lemma, we need the concept of type. So a type is a empirical distribution of a sequence, and type class is given by the sequence such that its empirical distribution is the given probability distribution T. The power set of X can be decomposed as disjoint type classes. And we use this to denote the uniform distribution of a particular type class. So the approximation lemma says that let rho X be is a CQ channel generated by a CQ channel. Here, the probability distribution is arbitrary. So the linear information of the channel with respect to an arbitrary probability distribution is no larger than the limit of this quantity. Here, we notice that for the n-channel use of the user of the channel, the distribution is uniform over a particular type class. So immediate corollary is that indeed the linear information of the channel, I mean that this quantity is the optimization with respect to the input P is equal to the limit of the right side. So with this, if we have the approximation lemma, then the proof of the height lower bound of reliability function is can go in the following. So for any integer m, we construct a CQ channel with respect to the optimal typical class in the approximation lemma. Yes, that means this channel is used m times. Then we can calculate the linear information of the m times m use of the channel. It is given by this formula by direct calculation. And then we apply the data compression protocol to the state rho m. And it said that by Renner's result, it said that for a rate, there exists a scheme such that this quantity holds. And then we convert the data compression code to channel code for NM. Here, the communication rate is given by this, and the error probability is upper bound by the data compression, by the error probability for the data compression protocol. So it goes, yes, this is the first protocol goes by, I think by this one, and then we can replace the rate. We can replace the rate for the data compression by the rate of communication rate Rm, and notice that this term minus the H alpha, the conditional entropy part, is the linear information of the N. with respect to a uniform distribution over a particular type class. And to continue, the reliability function is, this is the first line is the reliability function. And this equality holds for any function because the second line just take a subsequence of the first line. And then the equality comes here from the definition of the reliability function, because here that means we use the channel in k times. Of course, we can use we can decompose it as k times and k times n times, but the rate is multiplied by m. And for this one, we use the equality here, I think. And given this, and given this, let m tend to infinity, we obtain the lower bound asserted in the third one. So next is the sketch proof to the approximation lemma. Before the proof, we need some concept and some no result or Rene functions. The first is symmetric state. Let Gn be the permutation group and its natural unitary representation, or the tensor product Hilbert space is given by V pi. And then we define the symmetric state set by the state that commute with the unitary operation operator. So for any effect about the symmetric state is that for any symmetric state, there exists a universal symmetric state such that any symmetric state is no larger than the universal symmetric state up to a polynomial n. Here the equality is according to the operator. Yes, the order of the operator. There are some known facts. Indeed, these facts are lemmas or theorems or in the literature. So let's look at the facts. Rho xb is a general CQ state. And this is the Rene divergence. And this quantity is convex and non-increasing with the second state when the parameter in this is in this range. And the mutual information, the Rene mutual information defined all this state is given by this formula. And a good property is that the mutual information is additive, and it has a closed form given by this formula. And the Rene information of the channel, that take the optimization over the probability distribution P, is non-decreasing and continuous, and it is also additive. So with this we can we need additional lemma that roughly speaking that when we when we consider the Riemann mutual information of a symmetric state, the optimal part of B is I mean, the universal state is asymptotically optimal. So this is then having this, we can look at the proof of the approximity lemma. So the goal is to find a sequence of type classes such that for any probability distribution, the Riemann information of the channel is upbound by the limit of this quality. So first, this is the definition of this quantity, and this quantity use the additivity because it is additivity, and then of course here the equality B comes from that we can choose the universal symmetric state. And then the divergence, this function is expanded according to the union of disjoint type classes. And the equality D comes from that we can always select the optimal type class. Then we notice that I think here, yes. And then I think here should be the less than. Sorry. Yes, less than. And then to continue that, we can use the additional lemma that says that the universal symmetric state is asymptotically optimal up to a polynomial n. But here, when we take the logarithms and divide by n, we have this equality. So then this is the definition of I alpha. And then we let n tend to infinity, we obtain the desired upper bound. So so this is a brief summary of this talk. The conclusion is that we obtained the tight lower bound for the reliability function, thus resolves the long-standing whole-level conjecture in the affirmative. And we can show that the reliability function can be determined when the rate is above a critical value. As a byproduct, we provide the operational interpretation for quantum Riemann information of a channel in a proper parameter range. The open question is that can we derive the tight lower bound by the direct approach? I mean, by far we have no, we denote get this by the direct approach, but we believe there should some hidden trace inequality that can lead to the tight lower bound. And then having the reliability function for the CQ channels, can we consider the reliability for other channels? I think time is out. Yes, thank you very much.
Thank you very much. Any questions? Okay, so I have one question. So you mentioned as an open problem, considering other channels. So what would be the first candidate for further work? What kind of channel do you have in mind?
Other channels.
Yes.
Well, indeed, I think recall that whole level Schumack Westmoreland plays the role in quantum mechanics theory. I think the distinguished candidate is the entanglement-assisted classical communication through the general channel, because there we have the closed form for this setting. And if you look at the proof of this formula, it is established all the HSW theorem. Because here we establish the reliability for the CQ channel, we believe that, or we hope that we can apply the techniques to this setting to obtain the reliability function for the entanglement-assisted setting.
Okay, thank you very much. Any other questions?
So I have a question. So could you show me where you use the result of the quantum data compression with side information? Which part you directly use?
Directly use. Okay. This part? No. I think this part. Do you mean?
No, of course I understand. You consider this one, then you obtain some inequality, I think.
Yes.
So where you?
Because I think this is the result is based on the Reynolds lemma. This lemma says that, and indeed the lower bound comes from the duality.
This is a Reynolds result. Okay, I understand. Then how did you calculate the right-hand side?
Sorry, could you repeat?
How did you calculate that second line? So okay, I understand. Upper line corresponds to the error probability, error exponent. So then that second line marks alpha something. So this one can be calculated that's linear entropy. How did you calculate that second line? Could you show me that part?
No. I mean, because the second line is only related to the CQ state.
Oh, yes.
Of course, to obtain this result is the duality result stated in this paper.
Yes. So then you calculate the second line, I think.
Yes.
So where did you calculate?
Indeed, we need not to calculate this. We just notice the relation of data compression, the compression rate with the communication rate. They are related just by logarithm of the dimension. Okay, let me show you. Yes.
Of course, I understand. I'm asking the second line. This is the first line, I think.
Yes. Okay, maybe I can show you some appendix. Critical. Oh, sorry.
I don't think so. This is the main part, I think. Main part you already, yeah, this one. So,
Okay.
You apply in this way. So then, how did you calculate that quantity finally?
We just saw that it is lower bound by this, and the H alpha, the conditional entropy, is evaluated all Pacific CQ state.
CQ state. So then, okay, I understand. You calculate in this way.
Yes. I mean, we just construct the channel code from the M use of the channel, which is which generate rho M, a specific CQ state rho M, which can be applied the data compression. But the CQ state rho M is a specific CQ state in the sense that the classical part is uniformly distributed.
Okay, I understand. You answer my question. Okay.
Any other questions? Okay, so if not, we can thank the speaker again.
Okay, thank you.
Thank you. So this is the end of this session, and we will meet in 2 hours for the next session.